So the next session is on tools. The first talk is given by Ronak Buch, and it's on performance analysis and projections. Ronak is a PhD student in our lab, and he's been working on projections for a couple of years, and he'll give you more in-depth details about projections and show some examples of how to use it and what comes out of it.
Thanks for the introduction. Like Harshita said, my name is Ronak Buch. I'm a PhD candidate in the Parallel Programming Laboratory here. And today I'm going to talk about performance analysis in general, and more specifically projections, which is a performance analysis tool that we have in Charm++. So H.G. Wells once said that we must not allow the clock and the calendar to blind us to the fact that each moment of life is a miracle and a mystery. And he's right. Each moment of life may be a mystery, but each moment of a program shouldn't be. When we're trying to run things, we need to make sure that we measure stuff and get programs to run effectively and quickly and well. So I'm sure you guys are familiar with lots of these tools to do this in the serial world. One of the easiest things and one of the most basic things you can do when writing a program is just to time it. Things like clock get time of day, plain old Linux time will tell you how long an application runs for. There are also more advanced tools to profile applications, such as gprof, and then Valgrins, cache, and heap profilers, and different things like that. The trouble is that these techniques don't really work for distributed parallel programs. While they're useful metrics to measure, obviously we care about runtime, often when we're running things in parallel and we're running these big sophisticated applications, we need more information than what these serial tools can really provide us. Luckily, people have addressed and identified some of the problems in parallel performance analysis. So just to give you sort of a brief overview of what we're facing here, when you're running parallel applications, one thing that happens is that different processors will do different work. If we're running an MPMD application, it's intentional that different parts of the domain that we're running the application on will be doing different phases and be doing different sorts of computations. So we don't expect every processor to be doing the same thing. One thing that's radically different from serial computations is that we have a network now. So I know lots of applications are now connected to the internet and things like that, but in general, if you're communication bound in serial, you're probably not bound on the network. If we're doing things in parallel, the network now becomes a really big bottleneck, especially, as you all know, as the computation rate of CPUs has grown a lot faster than network speeds have grown in the past few years. So this is something that is completely ignored by lots of different serial profilers. Another issue is that load may not be balanced between processors. So even when we're doing the same thing on multiple processors, for applications such as weather forecasting or wave advection, or anything where we have differences in domain or differences in work distribution, we'll get different load on different processors we have in our job. Luckily, tool developers have identified these things and have worked on a few different applications to help developers work on performance problems they see in parallel programs. So these are things like MPIP, Vampire, HPC Toolkit, and of course, in our case, projections. These tools, as I mentioned before, provide details on communication performance of different applications, on how applications will scale at on different jobs and on different sorts of machines, how mapping affects applications, what the degree of load imbalance is, and different aspects of parallel performance like that. In particular, the tool that I'd like to talk about in detail today is projections. If you haven't used it before, projections is the performance tool that we've developed for Charm++ over the past few years. It identifies and gives analytical tools to work on a lot of the things that we just talked about, things like load imbalance, communication, and things like that. The way it works is that the Charm++ runtime traces application executions. So this happens just by a flag that you can build Charm with, and then a flag you can link applications with. And then you'll automatically get these performance logs that the runtime will capture for you. Then after you're done executing your application, you can get your logs, open it up in the projections tool, and then use them for local analysis, which then you can use to optimize and change your code in the future and then run again. So I'd like to give you a brief overview for those of you who aren't familiar with projections of sort of the different basic tools that we have, what they show you, and what kind of insight they can provide to your parallel applications. So the first one I'd like to talk about is a tool called Overview. So Overview basically gives you what the promise is. It gives you an overview of the entire execution. So here we see on the x-axis is time. On the y-axis is PEs. So PEs is processing elements, basically a notion of processors. The different colors you see are different entry methods. So you can see here that there are some evident phases. On the left, you have this green stripe, this green vertical stripe that it clearly has a barrier, something right after it. The black is basically unused time. So this big section of black in the middle, you can see that it's not quite vertical on the left edge, which means there's some load imbalance in the phase immediately preceding it. Some processors end before other processors do. So if we're going in and we're trying to do analytics on an application using this information, we can see that this is something that we might want to focus on. We might want to rebalance the load that we have. Another view that's very similar but slightly more detailed is timeline. Timeline is basically the bread and butter view of projections. It's very similar, but it gives you a little more information of the complete execution. So again, the x-axis is time. The y-axis is PEs. You'll see a few additional things in this picture. So for example, on the top of some of these PE lines, we have these little red ticks. The red ticks are user events. User events and different things like that are very important. Essentially what user events do in Charm++, if you're not familiar with them, it allows the user to insert calls inside their application, which adds instrumentation inside the logs. As a tools developer, we'd like to think, and we aim to add all the things that would be useful for an application developer for analysis to be in the tool. But of course, it's impossible to cover all the bases and every single thing that an application developer may find useful. So I think it's very important when you're developing these tools to be able to make them extensible and modifiable by the user. And I'll touch on that a little bit later on. Another thing you'll notice here are the colors. So as I said before, colors are different entry methods, but we can also color things in different sorts of ways. We can color by entry method, we can color by char, or the parallel object, we can color by frequency. So we should use different aspects of display to make it as easy and obvious for an application developer to figure out what is going on in their trace. One other thing that we can do in this that's very useful is that we can trace messages. So you'll see here, this is another timeline view for a different application. There are a bunch of white lines that are going from these little white ticks, which are message sends, to different entry method executions. And what this lets you do is find stuff like critical path in your application. It helps you find messages that are potentially slowing you down, and lets you trace the data flow of the application. Unfortunately, in Charm++, we don't have an explicit dependency graph, but we can sort of use this information to create one in an ad hoc way on the fly. And that's, again, something I'll touch on later on. Another tool we have is called time profile. So here on the x-axis, we have time. On the y-axis, we have essentially total execution. So here, time is bucketed into small intervals. And then you'll see that the different colors that we see on the graph are entry method executions again. So you can see that in a particular time, we have, in that bucket, we have an entry method executing for however high its bar is in that bucket. So again, we can see things like this big black chunk that's happening at the end of a phase. So it's very likely that this black chunk is associated with some load imbalance. So in fact, this is a run of Changa, and there was actually a serialization bottleneck that was happening here. So it's very easy to look at these things and to identify what is going wrong and give you pointers on what to actually look at. You can mouse over these sorts of things in the actual tool and see what functions you're executing and some more information about the logs that's actually captured. Another thing that's really important is to look at the same data in different layouts. So the view we just looked at was in the time domain. Here we look in the processor domain. So again, this shows you utilization in a certain time interval, but rather than showing you it across time, it shows you the load across processors. So this, again, lets you very easily identify load imbalance. So here it's not too bad, but the total utilization is pretty low. We have a lot of idle time, which is the white, and we have a lot of overhead, which is just the time above it. So here we can see that there's clearly some interference from a different application, or we're waiting on the network for something to happen. So there's still some issues here, but load imbalance, as you can see, isn't that bad. Everything is within 5% or so of each other. A third view of a similar thing is basically looking at the same thing in the frequency domain. So this is a little bit odd. So if you're unfamiliar, let me explain. The x-axis here is bin interval size. So essentially, these are different times that entry methods can be executing. The y-axis is number of occurrences. So what this means is that the bars you see on the left are how many times an entry method executed for a very, very short period of time. The little hump in the middle is the number of occurrences of entry methods that take sort of a medium amount of time. And this small bar on the right is a few entry methods that take a lot of time. So here you can see, even in your work units, you can't look at just the number of occurrences. You have to look at the weight of what they are. We can also look at this graph in a way where we weight the height of the bars based on the total time spent in every bucket. This just shows number of occurrences. So if we weight it the other way, the right becomes a lot larger because these are really long execution times, whereas the left will become smaller because these are very short execution times. But when you're looking at an application, this lets you see what distribution of work that you have. So this can help you identify things like grain size and what you should be changing to map well to the architecture that you're running on. So just to give you a brief overview, you have sorts of similar tools for network. So this is a communication graph in the time domain. We can also do these things on the processor domain and other similar ways. So in the network way, we can look at the particular spikes that we have in this graph. So this is, like I said, in time. The y-axis here is bytes received. So we, for example, see two big spikes over on the left, and the communication isn't really well distributed across the entire time interval. So here it's likely that we have some communication hotspots or bottlenecking going on. So maybe if we over-decompose more, we can send more smaller messages across a longer period of time and reduce the network bottleneck that we can see in this application. So those are sort of the basic projections views. We have a few more, slightly more advanced ones as well, things like multi-run analysis, user event view specifically, things like extreme analysis where we'll use the machine to identify particular areas of interest. But I won't go into all of that. Instead, what I'd like to talk about in detail are some of the more recent advancements that we've made in projections. So over the past year, we've added a bunch of different views and tools, and I'd like to discuss two of them in particular today. One of them is cache latency measurement, and the other one is communication thread tracing. So first off, cache latency measurement. This is work done in collaboration with one of our visiting students, Probia Roy and Xu Liu of William & Mary University. Essentially, the motivation here is a lot of the things we capture are at the macro level of functions, executions, and communication, and things like that. But in truth, a lot of the things that affect performance on parallel machines are the more detail-oriented parts of execution, such as caching behavior. Xu Liu has done some work in the past with HPC Toolkit that does similar sorts of things, and we decided that it'd be a good idea to do the same sort of thing in Charm. What we decided to do was use a sampling technique to trace accesses in applications and then attribute them to specific source lines in an application. The way we did this is by using a function of some of the new Intel processors. I think it's on a lot of Nehalem cores and newer, called PEBS, which stands for Precise Event-Based Sampling. Sampling is useful in this case because it's very low overhead. We're not getting every occurrence of a data access, but we're getting a lot of them and enough to give us insight into what the application is doing. Two of the important things about this is that when we take a sample, it provides the instruction pointer. So we know exactly which instruction was responsible for that data access that we got from the sample. And the really important thing here is that it also provides the latency of access. So rather than just getting a hit or miss count like PAPI would give you, this tells you how long a load actually took in the memory hierarchy. Now, this is something that didn't exist in older processors, so it's fairly new. So when we have this collected data, it lets us do a couple different things. One thing that we tried to do is get a spatiotemporal memory access pattern and latency graph. It doesn't really make that much sense right now. I'll explain it in a bit. We can also do more traditional things, such as a cache miss rate over time, and also a very useful thing, which is cache latency per source line. So it's a very, very directed tool that tells the developer what exactly to look at in their application. So one of the first things we did is kind of just explore the data that we could collect. So this is a visualization that's not actually from projections. We made this in R. It's sort of an exploration of what we could do with the different sorts of data. As a brief digression, I think one thing that we don't do well in projections right now is allow end users to develop their own analysis tools. As I said before, with user events, I think it's useful to allow users to add their own annotations. But if we formatted the logs better and in a more documented way, then enabling end users to be able to write their own analyses come up with better tools, and if they're general enough, even integrating them back into projections, I think would help a lot of developers rather than them fighting against the tools that we have if they're not perfectly suited for their application. Regardless, I think explorations like this are very useful because this let us see a couple interesting things. So essentially in this graph, on the x-axis we have time, increasing from left to right. On the y-axis we have essentially memory location. So as you can see here, there are two pretty clear regions. So we have a tree node region, this is an execution of Changa, and then we have a particle region on the bottom. So the tree node region fairly clearly accesses the same memory locations repeatedly over time. The particle region has a linear access pattern through time. So being able to identify these clusters of different parts of the application and how they access memory is a useful thing to be able to figure out what things to run when and how that affects caching performance. One thing that this graph also shows that you probably can't see, it's a little small, some of the dots are gray and some of the dots are red. The red dots indicate high latency. So these in particular will tell us when instructions are incurring high load latency and that we should be analyzing these things because there's potentially a conflict with something else or some cache misses that's happening because of poor data layout or conflicts with something else. We also use the same information to do more traditional things. So this just shows average cache miss rate over time. So again, as the projection view showed before, the colors here are entry methods. So you can see that particular entry methods over the entire execution have a fairly standard miss rate. That doesn't change too much. So maybe they're not loading everything into cache. Maybe there's size issues or conflict issues. The two black sections we see here could be good or bad. It's possible that the things that happen there are the code that's running there just always hits in cache. It's also possible that nothing's running there. But the good thing is that we can use the information we have collected here in concert with the other tools that we have in projections to figure out what code is running there and get more insight into what's actually happening. So in a lot of ways, we have to combine different aspects and different views of what we have. The third tool that we added for the cache performance stuff is source line tracing. So again, this picture is a little bit hard to see, but I'll try to explain it. So in the bottom left corner, essentially what we have are the different instruction pointers in our application and the number of samples and the load latency penalty that we get for each of those instruction pointers. You can switch between L1 hits, L2 hits, LLC hits, and misses. When we sample, we get all of these results. Using this, we can then click directly on one of these lines, and we get taken to the source code with the exact source line highlighted. So you can see the three bold lines in the text up there. So this usually fairly clearly will tell you that you have some sort of pointer in direction, or you have some access pattern that's getting into parts of memory that you probably shouldn't be. So basically, you can use this information to redirect how you do your layout. So you can do AOS, SOA style transformations. This will also alert you of things like NUMA effects that happen in memory you've allocated. But basically, this will tell you very specifically that these are the lines in your application that are getting poor cache performance, and these are what you should look at. And it's a lot better to get this sort of impact, especially when it's not just a miss, when it's also a measure of what the cache contention is, because you get the total latency. So you can see whether there's pressure from other parts of the application as well. It's another interesting thing that we discovered from this is that when you run the same application in a strong scaling sort of way, when you reduce the data on every core, the cache performance will change quite dramatically. And getting this sort of insight into how fast the cache is actually working for different sorts of loads can yield some very interesting data for that sort of analysis. Another tool that we added in the recent year is communication thread tracing. So this is work with Keshav Santanam, who's one of the undergrads in PPL. And essentially the motivation here is that we wanted to do this very detailed network-level analysis of Charm++ applications. So in Charm++, there's a mode called SMP that some people have talked about in previous talks. To give you a brief overview in case you've forgotten, in SMP mode, essentially we have processes that have worker threads and a communication thread. Often the trouble for these things is that you have a certain number, you have n worker threads and a single communication thread per process. So sometimes the communication thread can become a bottleneck. More specifically for this, the communication thread handles all the communication. So we get a very detailed view of just the network part, and we can remove the application and runtime sorts of parts of the communication stack. We can just look at the network communication. And the motivation essentially is to measure and analyze this in isolation. So we can remove the queues, remove the copies, and things like that. So as long as you build with enable tracing com thread, you'll get this information in your logs, and then you can just run it in a normal Charm++ program. So we have a few different tools to use the data that we've collected. Essentially, what we've done is figured out the metric of excess network latency. Unfortunately, this graph is very hard to read, but I'll tell you about what it's actually trying to display. So there's yellow bars that we have here that essentially show the minimum communication time for every message size sent over the entire execution of the application. What this basically tells us is what the maximum observed performance is for every size message that we sent in the application. We're going off of the assumption that the maximum performance that we see, so lowest latency, is close to the practical peak of the network. This is potentially a spurious assumption, especially on machines that don't give you contiguous allocations. But the thing is, it lets us do this without any sort of training offline, and we get real data when we're looking at the network performance. Then we compare that to the latency that we observe for every message in the application. And then we measure the excess. So we measure what we observe that's above the minimum for the entire execution for all sends of that particular size. And the conclusion here is that anytime that we see a lot of excess message latency, it's because of something on the network, either an oversubscribed link or a hotspot in a router or something like that. Another thing that we've added on the bottom here is that the user can also provide an alpha-beta model. So if you have a model for your network for latency and bandwidth, then we'll also just trace that and see how close the network performance you're getting is to your theoretical model. One thing we'd like to do here is correlate these things with the timeline to see if bottlenecks that we see at a particular time also correlate to delayed messages and bottlenecks that we see there. And this also gives us a quantitative report for different sorts of topology mappings. So if we run the same application in different topology mappings, we can see that some of them might have a lot of excess latency, some of them may have less excess latency, some of them may have different distributions of excess latency. But this gives us another sort of quantitative metric on trying to figure out how topology-aware mapping affects different applications. We also have a few tools to help developers use this tool. So rather than showing the entire thing in the time domain, now we've just selected the top 100 messages with excess network latency. So again, this is just a sort of a directed way to allow the analyst to find out which messages are actually slow, and then we can look at these and correlate them with things in timeline. But switching the domain like this and using the machine to do search is a very useful thing. Forcing the user to do everything manually and to sift through mountains and mountains of data is kind of foolish when we have a computer that can do everything much, much faster than us right in front of us. So we should definitely allow the machine to find data in the logs that we've collected. And that's something that we haven't done very well so far in projections, but we're starting to add it to more of our tools. Finally, we added communication thread tracing box and whisker plots. So this is for the entirety of the execution. We see the distribution of latencies for every COM thread in the application. So in this small execution with just 2 threads, we can see that the median on the communication thread on the right is much higher than the median for the communication thread on the left. So this could be a variety of reasons. But there's probably some sort of contention or issue affecting communications for this PE. So given the rest of the information that we have, we can now use this to analyze why these things happen. And also being able to see the outliers and maximum and minimum range can give us a nice overview of what is happening on the network. One of our hopes for this is that when we're running things on machines that don't give us contiguous allocations, we can see COM threads that are on the border, or will often send messages through other parts of the application, and be able to very directly see if the excess network traffic is affecting our performance for particular communication threads. So we have a lot of future work we'd like to do with this. One thing is to identify communication thread oversubscription. So as I said before, we use this to get very detailed network analytics. And we do this by ignoring the rest of the logs other than the communication thread logs. But if we add in the other logs, now we can see the total message pathway from a particular PE to that's communication thread, across the network to the other communication thread, to the final PE. So getting this sort of thing will let us see if communication threads are oversubscribed. If there's a big gap between when chars try to send messages and when they're actually sent, then we know that maybe we're running with too many worker threads per comp thread. We can also estimate the runtime given an ideal network. So essentially, if we take all the messages that we send and we take out the excess latency we see, then we would see what it would look like if we had a perfectly mapped job that never had any contention. So this can essentially give us an upper bound on what an ideal topology-aware mapped execution should look like. And as I said before, we also want to use topology and routing information to identify different sort of network hotspots that we have in the application. So just as a brief overview of some of the things we've talked about, when you're writing an HPC application and you're trying to get good performance, it's critical, really vital that you use a performance analysis tool. At the scale and complexity of the applications that we develop and run today, it's extremely difficult to get any useful information without using some sort of tool. If possible, reduce the overhead of measuring different sorts of detailed metrics. Using things like sampling and using existing logs to derive new data can provide a lot of insight without putting a lot of extra workload or interference to your application. When you're developing tools and views, it's vital to make things as obvious as possible. It's easy to get confused and to go down false paths when you're doing this sort of analysis. And making everything very lucid and very clear really helps developers and saves a lot of time. Finally, it's worth making it possible for users to write different sorts of ad hoc analysis tools. Making sure things are documented properly and allowing users to add on different sorts of annotations into logs and into different sorts of tools. Allow them to expand the scope of what they're looking for and customize the tool for their particular application. And that can be very useful for particular domains. And it's a lot better, it's a lot easier to get users when they can sort of take your things and make them work for them rather than forcing them into whatever you've designed in isolation. So that's all I have. Thanks for listening, and I'll take any questions if you have them.
Do you synchronize the timers across all the processing elements?
So on some machines, they're synchronized already. On other ones, we have ways to synchronize them in analysis. So we don't synchronize them in the logs, but then we can adjust them in the tool that we have. So we have ways to work around that when they drift and when they aren't completely synchronized.
Do the network latency analysis tools work for non-com thread builds?
No. So right now, they require a com thread log to exist.
Thank you.
Have there been attempts to estimate the overhead of using projections?
Of projections? Yeah. So it's very easy to run something with and without projections. In general, the overhead's not too high. It varies per application. Really, it depends on how big your logs get. Often, the biggest thing for interference we see is when it writes to disk. If it writes to disk very frequently, then we can get a high degree of overhead. And it's very obvious when you're looking at a timeline, you'll see these big swaths of nothing, basically where it's writing out to disk. But in general, it's not too high. It's basically just timers and then creating that into some data structure. So it's not nearly as high as lots of different tracing things. It's sort of on the order of sampling. It's a few percent.
Color-wise, you always only split through entry methods. Is there is there an option to specify further domains, smaller domains, to decompose your analysis?
So yeah, by default, sort of the intention of projections is to work on the entry method scale. So you can run something like gprof and get particular method granularity automatically. But in general, if you want that sort of granularity in projections, you'd use bracketed user events, which you can put before and after function calls or before and after any regions you want to analyze in your logs. But those aren't detected automatically because they don't have any relation in the runtime system. but it's simple enough, and people have often added these user events to do things like that.